This is the science behind one of the strangest fishing baits ever invented, a microwaved hot dog soaked in Kool-Aid. And what makes it fascinating isn't just that it works. It's what happens underwater after you cast it in. The invisible chemical plume spreading through the water column, and the biological machinery channel Catfish, Ictalurus punctatus, used to track it down. In some experiments, hot dogs attracted catfish within 60 seconds of hitting the water. $3, 5 packets of Kool-Aid, a handful of cheap hot dogs, 45 seconds in a microwave, and somehow this combination has become one of the most viral catfishing methods on the internet. The reason it works has almost nothing to do with luck, and everything to do with fluid dynamics, amino acid chemistry, and one of the most extraordinary sensory systems in the animal kingdom. Start with the bait itself. The standard recipe calls for 5 packets of red Kool-Aid, about 5 to 6 tablespoons of garlic powder, and hot dogs cut into 1-inch chunks. You add a cup of water, mix it together, and let the pieces marinate. Cherry, tropical punch, and grape consistently rank as the top-performing flavors, with a good ratio being 2 packets of Kool-Aid per 3 hot dogs. Some anglers go further, adding vanilla extract, anise oil, shrimp flakes, or menhaden oil. Others have experimented with Jell-O and vegetable oil combinations, but the core stays the same: hot dog, Kool-Aid, garlic. Now the microwave step. And this isn't random. When you microwave a hot dog for about 45 seconds, you evaporate a significant portion of its water content and shrink the proteins. The Maillard reaction begins to alter the surface proteins, creating new aromatic compounds, while the heat drives moisture outward. The result is a rubbery texture that grips a circle hook far better than a raw hot dog ever could. Experienced anglers have found that the cheapest, highest fat content hot dogs work best. The microwaving gets the juices flowing, intensifies the aroma, and creates a bait that won't slide off your hook on the cast. It's functional engineering disguised as a kitchen shortcut. But here's where it gets genuinely interesting, because the moment that bait hits the water, chemistry takes over. Call to action: like the video and subscribe. A hot dog is not just processed meat. A single 1.5-ounce hot dog contains 7 grams of complete protein, meaning it carries all essential amino acids. Its profile includes 2 grams of alanine, 3 grams of arginine, 9 grams of glutamic acid, and 3 grams of proline. Those names might not mean much to you, but to a catfish, they're a dinner bell ringing across hundreds of feet of water. Electrophysiological studies on channel catfish have identified L-alanine and L-arginine as the most stimulatory amino acid compounds, with estimated detection thresholds of approximately 10 to the negative 9th molar. That is an almost incomprehensibly small concentration. The catfish taste system has distinct receptor sites specifically tuned for these amino acids, and for triggering the biting and snapping behavior that actually gets a fish on your hook. L-arginine is the most effective stimulus at low concentrations, with a behavioral threshold of just 3 times 10 to the negative 7th molar. Multiple exposures to L-proline and L-alanine at higher concentrations provoked up to 25 bites per test in laboratory settings. A hot dog is essentially a delivery system for the exact chemicals catfish are hardwired to hunt. Now layer in the Kool-Aid. Kool-Aid is designed to dissolve in water. That's its entire purpose. A powder engineered to disperse evenly through liquid, carrying flavor and color as it goes. When you soak a hot dog in it and drop it into a river, the Kool-Aid acts as a scent carrier, pulling amino acids, fats, and garlic compounds outward into the water column. The sugar and citric acid in the mix further boost the chemical signature. You've essentially weaponized a drink mix. And this is where we track the plume. The formation of an attracting odor trail follows a chain of events: the emission of the attractant from the bait, turbulent mixing into the immediate surroundings, and then downstream advection and dispersion by the current flowing past. The theory behind plume dilution has been well developed for atmospheric plumes, and those results apply directly to underwater plumes as well. What's critical to understand is that the plume isn't a smooth, even cloud. Previous experiments on odorant dispersion in both air and water have shown that the instantaneous concentration structure is highly filamentous, meaning thin ribbons of scent surrounded by pockets of clean water. As these filaments are carried downstream, turbulence stretches and distorts them. The odorant diffusion coefficient, the rate at which scent molecules spread outward through the water, determines how wide those ribbons grow and how quickly they weaken with distance. The statistics of those filaments, their concentration, their spacing, their width, all shift with time and distance from the source. Environmental factors shape everything. Temperature, current, and depth determine how far and how fast scent molecules travel. In still water, scent disperses slower and more evenly. In rivers or moving water, it travels downstream quickly, creating a long, narrow corridor of detectable chemistry. Warmer water accelerates diffusion, potentially shortening the bait's effective range but intensifying the near-field signal. Colder water slows things down, extending the plume but weakening it at any given point. Research on optimal bait presentation found something elegant. The initial concentration in a plume depends on the ratio of surface area to cross-section of the bait. To use a given amount of bait optimally, you divide it into relatively small pieces. That 1-inch chunk size isn't just convenient, it's close to ideal for maximizing scent output. So the plume is out there, threading through the current in invisible filaments. Now the catfish enters the picture. Researchers have described catfish as swimming tongues, and that description barely does them justice. A channel catfish, Ictalurus punctatus, possesses over 140 sensory pads dedicated to smell, compared to roughly 10 olfactory membrane folds in a largemouth bass. They carry 2 pairs of nostrils used solely for smelling, allowing them to detect compounds at concentrations as low as 1 part per 10 billion, the equivalent of a single drop of scent in an Olympic-sized swimming pool. But smell is only half the story. The average catfish has 175,000 taste buds, part of a gustatory system that scientists consider the most sensitive known among all vertebrate animals, distributed across its entire body, from barbels and lips all the way to the caudal fin. Those barbels, the whisker-like sensory organs projecting from the fish's jaw and snout, are essentially mobile taste arrays, allowing the catfish to sample water chemistry in every direction simultaneously. Over 20,000 taste buds are internal, and more than 100,000 are external. They can taste your bait without ever biting it, detecting flavor at distances up to 15 feet. Channel catfish can sense certain amino acids at concentrations as low as a teaspoon of chemical dissolved in a 1-acre pond, averaging 3 feet deep. Blue catfish and flathead catfish share this same extraordinary gustatory architecture, but Ictalurus punctatus has been the most extensively studied, and its sensitivity benchmarks are among the highest recorded in any fish species. When a catfish encounters that filamentous plume of Kool-Aid-infused chemistry, it doesn't just smell food, it reads the plume like a map. Current research from the California Institute of Technology has explored how aquatic organisms use turbulent plume structures for navigation. Following concentration gradients upstream toward the source, the catfish moves through alternating pockets of scent and clean water, comparing signal strength across its barbels, adjusting course in real time. In some experiments, hot dogs attracted catfish within 60 seconds of hitting the water. There's a persistent myth that catfish prefer rotting, stinking bait. The science tells a different story. While small catfish may bite stink baits, larger catfish respond to fresh amino acid-rich presentations. The Kool-Aid hot dog works not because it's pungent or foul, but because it's chemically precise, delivering exactly what catfish taste receptors are scanning for, carried by a dissolution system engineered for rapid, even dispersion. $3 worth of gas station hot dogs and powdered drink mix, a kitchen microwave, and underwater, a chemical event that exploits fluid dynamics, amino acid biochemistry, and 200 million years of sensory evolution. The catfish doesn't care that it looks ridiculous on your hook. It only knows that somewhere upstream, the water just started speaking its language.